Hello, everyone. Today, I'm introducing you to iTFlow, a cutting-edge software tool designed to revolutionize cardiovascular diagnostics through detailed flow analysis. This tool allows us to visualize streamline pathlines, calculate flow rates, assess wall shear stress, and evaluate energy losses within the cardiovascular system, among other useful tools. These tools can be used to evaluate blood flow of different diseases such as aortic valve stenosis, which we'll be using as an example throughout this presentation. To begin, let's start with streamlines and pathlines. Streamlines help us see the direction of blood flow at every point, providing a snapshot of flow patterns during different cardiac phases, particularly systole. Between the healthy volunteer and the stenosis volunteer, the healthy volunteer's streamlines depict low velocity of blood flow throughout the aorta, while the stenosis volunteer has an area of higher velocity. Pathlines trace the trajectory of individual particles over time, offering a dynamic perspective on fluid movement. Utilizing pathlines, we can gain a more detailed visualization of flow. For example, when differentiating between a healthy and stenosis volunteer's ascending aorta, we observe that the healthy volunteer has unidirectional pathlines, while the stenosis volunteer forms a vortex. The rapid increase and decrease in the graph's flow rate represents the heart's forceful contraction and relaxation phases. The software can calculate several different parameters, including flow rate and regurgitant volume. These measurements are crucial for diagnosing and assessing the severity of valve insufficiencies, conditions characterized by some blood flowing backward rather than progressing forward into the systemic circulation. This comprehensive analysis helps us understand the efficiency of cardiac output and also identifies potential abnormalities in heart valve functions. In this example, not only does the healthy volunteer have a higher flow rate, they also have a lower regurgitant fraction. Understanding wall shear stress is equally as crucial as it reflects the tangential force exerted by the fluid on vessel walls, which can influence vascular health and disease progression, specifically by increasing energy loss. The turbulent flow depicted previously causes an increase in stress in the stenosis volunteer as compared to the healthy volunteer. Energy loss analysis within iTFlow allows us to pinpoint areas where blood flow resistance is unusually high, leading to increased cardiac workload. This insight holds great potential for diagnosing and managing conditions that might not be visible through traditional imaging techniques. In our observation of streamlines during systole for a healthy volunteer, we identify key patterns in blood flow. The streamlines show a consistent and smooth flow pattern through the aorta. The flow velocity is 1.5 meters per second or less, indicating normal unobstructed blood flow. The corresponding flow rate diagram supports this with a peak flow rate that aligns with healthy cardiac function. However, for patients with aortic valve stenosis, we notice significant differences in the streamline compared to the healthy volunteer. The streamlines in the area around stenosis display higher velocities, greater than 1.5 meters per second, indicating restricted blood flow due to the stenosis. This is evident from the flow rate diagram, where the peak flow rate is similar, but the distribution and persistence of high flow velocities point to the presence of stenosis. Such findings highlight the impact of stenosis on blood flow dynamics. This slide focuses on the concept of energy loss during systole for a healthy volunteer. The visual representation and corresponding graph illustrate a flow velocity of 1.5 meters per second or less, correlating to minimized energy loss. The graph shows the energy loss over time, with an average energy loss of 2.09 milliwatts and a maximum of 7.14 milliwatts. These values indicate that the heart is working efficiently, with minimal energy loss. This slide highlights the increased energy loss during systole for a patient with aortic valve stenosis. The visual representation shows that the flow velocity exceeds 1.5 meters per second, leading to increased energy loss. The graph displays significantly higher energy loss over time, with an average of 6.27 milliwatts and a maximum of 28.10 milliwatts. This increased energy loss indicates that the stenosis patient's heart has a greater workload, increasing the risk of additional heart diseases in the future. Thank you for being here. I invite you to explore more about iTFlow and see firsthand how it can be integrated into your practice.